Today we're going to talk about the mole. A mole in chemistry is a concept that many students have a difficult time understanding, but in actuality, the word mole is very similar to another word that we're very familiar with, and that word is dozen. If I tell you to go get me a dozen marbles or a dozen bowling balls, you would go get me 12. If I asked you to get me a dozen of anything, you would get me 12 of them. A dozen is simply a number. You have no trouble at all understanding that a dozen marbles and a dozen bowling balls do not have the same mass. They don't take up the same amount of space because one marble and one bowling ball are very different from each other in both volume and mass. Well, a mole again is a very similar term. It still stands for a number. Now, the number is much bigger. The number is huge. It's so big that we really have trouble comprehending just how big it is. But a mole, as it says here, is equal to 6.02 times 10 to the 23rd of something. So if I asked you to get me a mole of marbles, you'd go get me 6.02 times 10 to the 23rd of them. That's 602 with 21 zeros after it. Very, 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 very large number. This number is called Avogadro's number, and we use it in many kinds of calculations in chemistry. So when I tell you that I want you to go get a mole of something, whatever that substance is, you're going to go get me 6.02 times 10 to the 23rd of them. And if you're dealing with carbon atoms versus the sodium chloride or carbon dioxide molecule or particle, you would get me something that was very different in both mass and volume because one carbon atom is very different in mass and volume than one carbon dioxide molecule. So what do we talk about in terms of amounts of these substances and representative particles? Now remember, an element has a representative particle of an atom. That's the smallest particle you can have of of carbon that still has the characteristics of carbon, that can still be identified as carbon. So if we want to get a mole of carbon, we would say that we would get 6.02 times 10 to the 23rd atoms of carbon. On the other hand, if we wanted to get a mole of sodium chloride, remember sodium chloride is an ionic compound, and we talked before about the fact that an ionic compound is represented by formula units. Then you would go get me 6.02 times 10 to the 23rd formula units of NaCl. And a formula unit, 6.02 times 10 to the 23rd formula units of NaCl would be very different in both mass and volume from 6.02 times 10 to the 23rd atoms of carbon. One carbon atom and one formula unit of NaCl are different in mass and volume. So a mole of each of them would be very different as well. A mole of carbon dioxide, which is a molecular compound, and remember molecular compounds are made up of molecules. They are individual molecules, very different from the lattice structure of something like sodium chloride and other ionic compounds. But still, if you wanted a mole of carbon dioxide molecules, you would be getting 6.02 times 10 to the 23rd of them. If we want to determine how much one mole of a substance weighs, or how much the mass of one mole of a substance is, we sometimes call that the molar mass or the formula mass or the gram formula mass. We use the combined atomic masses of the atoms that make up the substance. Now take for instance the atomic mass of copper. Now the atomic mass of copper, we're talking about the mass of one atom of copper. We're going to look that up on the periodic chart, and we look it up on the periodic chart, And although it's kind of fuzzy here, if you look at your fold out chart that you have and look on the outside, you'll see that the atomic mass of copper is 63.546 AMUs. Now, that is not the number that I want you to use. In fact, I'm just going to go ahead and make that green because I don't want you to write down all of the values that are given for the atomic masses. I always want you to round to 2 places past the decimal. So anytime that you get a value off the periodic table, I want you to round that to 2 places past the decimal. So in the case of this particular compound here, or excuse me, in the case of this particular value, I'm going to draw the line after 2 places past the decimal. Look at the very next digit, it says to round up. And the value that I'm going to record for my answer is 63.55 AMUs, atomic mass units. So that's the answer that I want. Notice I did not put that in scientific notation. I don't want scientific notation for our molar masses, or for any of our atomic masses. I want those in standard notation. Now, if we want the molar mass of copper, they very nicely did something. They said that the molar mass of a substance, or 1 mole of copper in this case, was going to be the exact same numerical value as the atomic mass units, so 63.55 grams. Now, we could never weigh out 63.55 AMUs, but we can certainly go back to the balances in our laboratories and weigh out 63.55 grams. Likewise, if we want to find the atomic mass of silver, that's the mass of 1 atom of silver. We look it up on our periodic table and look at your fold-out charts on the outside, and that number says that the atomic mass of silver is 107.868. Remember, I want that 2 places past the decimal, so draw your line. I don't care if you've got a line drawn after 2 places past the decimal on every single block for every single element on that periodic table. I want you to know how to round it to 2 places past the decimal. Since that next number is an 8, we're going to round up that 6 to a 7, and we end up with 107.87. And remember, it's for 1 atom, so the very tiny units of AMUs, atomic mass units. Therefore, if I'm going to find the mass of 1 mole of silver, the molar mass of silver, I'm going to have the exact same numerical value. It's simply going to be in grams. So that's all we have to do to find the mass of 1 mole of a substance is look up its atomic mass on the periodic table and write it down in terms of grams. So what happens if it's more than just a single atom? Well, let's look at O2. First of all, if you look up oxygen on the periodic table, oxygen is 15.9994. So with that 15.9994, I'm going to keep showing you, so there should be another 9 and a 4. I'm going to keep showing you how we're going to round these because I want to make sure that you're getting these rounded correctly. So we're going to draw our sig fig line, draw our line 2 places past the decimal. That 9 says round up. So when we round up that value, that's going to take it all the way up to 16.00. In order to get the molar mass of oxygen, think about what we did in the last set of notes. We said that what makes up that particular substance is 2 oxygens. Those 2 oxygens, each oxygen weighs 16.00 grams per mole each, which is going to work out to be 32.00, 2 places past the decimal for that value. Now, the way I want this recorded is not only rounded 2 places past the decimal, but the correct terminology for molar mass is grams per mole. So in both of the cases up here, since I'm dealing with molar mass, even though it's just an atom, I still want grams per mole as well for the units for these. What about for sodium and chlorine? Well, yesterday when we were doing this, we said that there was 1 sodium in NaCl and 1 chlorine, and all you're going to do is put a plus in between there. And I've got to see this. If I don't see this, you're going to get it wrong because I want to see this work. We've got 1 sodium and 1 chlorine. If we look up sodium, sodium is, if you look it up on your chart, is 22.9898. 22.9898. I'm going to do another couple of them up here. We're going to draw that line 1 place, or excuse me, 2 places past the decimal. That 9 says to round up, so the molar mass is 28. I'm sorry, it's not 28.98. It's 22.9898. So 22.99 for our molar mass of sodium. So we've got 1 times 22.99. I'll get my colors right in just a second. 1 times 22.99. Chlorine is 35.453. So if we have 35.453, I'm getting this pretty scrunched together over here, and we draw our line right after the second place past the decimal, we'll see that in this case we don't round up. So our molar mass is simply 35.45 for chlorine. Now, you could plug this into your calculator as 1 times 22.99 plus 1 times 35.45 and hit enter and get that value, but obviously the ones don't matter. When you multiply anything by 1, it's itself. So all you really need to do is add these two together, but either way, you're going to come up with 58.44 grams per mole for the molar mass of NaCl. Now I'm going to erase these values so that we can look at these next few questions. H2O, we've got 2 hydrogens, and we've got 1 oxygen. Remember, I want to see the plus in between. Hydrogen is 1.00795. We're going to draw our line after 2 places past the decimal. The 7 says round up, so this becomes 1.01 for hydrogen. So hydrogen is going to be the 2 times the 1.01 plus 1 times, and we've already done oxygen, I'm not going to do it again, 1 times 16.00. Again, plug it straight into your calculator. You don't have to hit enter until the end because your scientific calculators will do order of operations. 2 times 1.01 plus 1 times 16, and you end up with a molar mass for water of 18.02. I hope you're practicing this in your calculator as I'm doing it so you make sure that you're getting the same values that I'm getting. It's important for you to get these, to make sure that you're using your calculator correctly. Now the only new molar mass that we're going to deal with in the next one, NaNO3, is nitrogen. Nitrogen on your chart is 14.0067. So if we have 14.0067 and we do our line right past the second place past the decimal, that next digit says round up, So we're going to get 14.01 for a molar mass for nitrogen. So let's see how that plays out in this compound. We've got 1 sodium, we've got 1 nitrogen, we've got 1 oxygen, excuse me, 3 oxygens. Gotta watch me like a hawk. And remember, what do we put between each one of those? I hope you're putting a plus sign, because if you don't follow this pattern and multiply, then add 1 sodium plus 1 nitrogen plus 3 oxygens, I have so many students that will multiply those numbers and get outrageously high molar masses. So be sure that you're putting pluses in between those values. So sodium we've done, 22.99. We just did nitrogen at 14.01, and we've already found oxygen at 16.00. So those are the values that we should plug into our calculator in that order. 1 times 22.99 plus 1 times 14.01 plus 3 times 16. And when we get our answer, it should be 85.00 grams per mole. 1 mole of NaNO3 weighs 85.00 grams. So let's look at our final one here, aluminum sulfate. We've got a couple of different elements in here. If we look up aluminum, aluminum is 26.9815. That's the molar mass for aluminum. I hope you're looking these up on your chart and making sure you're seeing these values and where they're located. When I draw the line, I see that the very next digit says don't change anything. That 8 stays the same, so we end up with 26.98 for aluminum. Sulfur, when we look it up on the chart, is 32.066. Draw the line after the second place past the decimal. That 6 says round up, so we're going to get 32.07 for our molar mass for sulfur. So when we show the work for doing this molar mass, for finding the molar mass of aluminum sulfate, we see that we need 2 aluminums plus 3 sulfurs. Remember, if there's no number after the element, it's an understood 1. And then once we multiply it by the 3 outside the parentheses, that's going to tell us that we have 3 sulfurs. And 3 times 4, we have 12 oxygens. Make sure you're multiplying by outside those parentheses. So now we see we have 2 times 26.98, and we're going to plug it in the calculator just like this, plus 3 times 32.07, plus 12 times 16.00. And if you did this correctly, you should end up with 342.17 grams per mole.